Now let's get on to the radial part of the equation, which is arguably the most important part, as this gives the energy levels of hydrogen atom, or for that matter any atom. Now the time independent Schrödinger equation for an electron of mass m in a Coulomb potential is given by here, the Schrödinger equation, and our radial function is here, and this is the kinetic radial part here, and this is the Coulomb potential, as said. And first here we multiply by minus 2m over h bar squared and rearrange to get this equation. And for convenience, we remove the first derivative term by defining u sub r equals r sub r. And then the radial equation for u of r becomes a 1D Schrödinger-like ODE here. Now, bound states and energy, we introduce parameters for a bound state where E is less than 0 and define the Bohr radius as here, 4 pi epsilon naught over h bar squared over m E squared. And we also define kappa equals square root of minus 2m E over h bar, where kappa is greater than 0. In terms of the Bohr radius, the Coulomb coupling is here, which when we substitute into the equation, it becomes this. Now we will solve ODE for u sub r, that's finite at r equals 0, and normalize for u goes to 0 as r goes to infinity to make equations dimensionless, and define rho as equals to 2 kappa r. Another equally common choice would be rho equals 2r over n of the Bohr radius. And we insert kappa equals 1 over n over the Bohr radius, rewriting the derivatives as such here, where d by dr equals 2 kappa d by d rho, and d squared over dr squared equals 2 kappa squared, and d by d rho squared. The ODE becomes dividing through by 2 kappa squared here, d squared u over d rho squared, plus etc, with this beta term coming into it here, where it's beta is equals m e squared 2 pi epsilon naught h bar squared dot 2 kappa, which equals 1 over 2 kappa and the Bohr radius here. And we're using rho as 2 kappa r. We find beta equals 1 over r, rho, so scaling, but we will proceed with standard substitution method. And asymptotic behavior, as r goes to infinity or rho goes to infinity, the dominant term is minus kappa, so u is approximately is an approximation of e to the minus kappa r, or similar, I think the actual word for this is. For a normalizable solution, now the growing exponential is non-physical, as r goes to 0 or rho goes to 0, the centrifugal term is approximately L plus 1 over r squared, and it dominates, so u is rho to the L plus 1. The r to the minus L solution is singular at origin. These suggest that an ansatz equal to u sub r equals to r L to the L plus 1 and e to the kappa r v r, or dimensionless variable rho, where u sub rho equals rho to the L plus 1 e to the minus rho over 2 v rho. Plugging these into ODE transforms it into an ODE for v sub rho. After some algebra and collecting terms, we divide by a common factor, and we obtained a confluent hypogeometric differential equation here, And we write parameters lambda equals beta over kappa minus L minus 1. The standard confluent hypogeometric form is here, whose regular solutions are the associated Laguerre functions, where n is the non-negative, kappa is a non-negative integer. To get physically acceptable normalizable V's of rho, we need solutions to terminate as a polynomial, otherwise V times e to the minus rho over 2 will become like e plus to the plus rho over 2 times a power series and diverge. Termination requires that lambda equals n sub r, which is with n sub r equals 0, 1, 2, where n sub r is the radial quantum number, the number of nodes in the radial wave function. Using definitions and solving for kappa and hence energy gives the quantization condition and well-known energy spectrum. Now please like and subscribe.